Today I'll be proving that in a vector space, if a spanning set of vectors has the same size as a basis, then the spanning set is also a basis. Okay, so what I'll do is I'll make v1, v2, the vectors v1, v2 up to vm. This will be the spanning set. And I'll make w1, w2, wm as the basis. And since it's a basis, it will both be spanning and also linearly independent. Okay, so now since the v's are spanning, what I'll do is write each of the w's in terms of the v's as a linear combinations. So we can write w1 as equal to a11 v1 plus a21 v1 plus dot 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 plus am1 v1. w2 we can write as a12 v1 plus a22 v2 plus dot 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 plus am2 vn. I should say, wait, vm and vm. Okay, and dot 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 wm we can write as a1m v1 plus a2m v2 plus up to amm vm. Okay, all this information can be represented in the following matrix: w1, w2. So a row of all the w's is equal to a row of all the v's, and then we have a matrix which has all our a's. Okay, so here's our square matrix m by m. This is matrix A. We'll call this matrix W and call this matrix V. So to see how this works, as an example, the entry W1 is equal to, and doing matrix multiplication, we have A11 V1 and we have A21 V2 plus dot 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 and up to AM1 VM. So that's just an example of how the matrix, how we convert these equations into this matrix equation. Okay, so we have W equals VA. Now I'll prove that A is invertible. So it's an m times n matrix, and I'll prove why A is an invertible matrix. So if we assume, for the sake of contradiction, A is not invertible, it means when it's row reduced, when we do Gaussian elimination on A, it will have at most m-1 pivots / leading columns. So when we do row reduction, it will have at most m-1 pivots / leading columns. This means there will be, when we solve the homogeneous equation Ax equals 0, there will be at least one column corresponding to a free variable. And since there's a free variable, it means there exists a non-zero vector C which satisfies AC equals 0. So we have a non-trivial solution to the homogeneous equation Ax equals 0. So now we'll let C equal to C1, C2 up to Cm. And now what I'll do is, since W is equal to VA, I'll multiply both sides by C. And using associativity of matrix multiplication, we'll have V times AC, which is equal to V times 0, which is equal to 0. So that means WC equals 0. And WC is equal to W1, W2 up to Wm times C1, C2 up to Cm. This is equal to C1, W1 plus C2, W2 plus plus Cm, Wm equals 0, 0 vector. However, since the W's form a basis, so it's linearly independent, which means the only way for linear combination of the W's to be 0 is if all the C's are 0. That means all the C's are 0. However, this contradicts from earlier, where we found there exists a non-zero C satisfying AC equals 0. So this is a contradiction, and we can conclude using proof by contradiction that A is invertible. And we'll let B equals the inverse of A. So using W equals VA, we can multiply both sides by B, the inverse of A. And this is equal to V times AB by associativity, which is V times the identity matrix, which is equal to V. So now W times B equals V. So now what we have to prove is that the V's are linearly independent. Okay, so what I'll do is assume the V's are not linearly independent for the sake of contradiction. So doing another proof by contradiction, that means there exists values d1, d2 up to dm, which are not all 0. So exist real numbers from d1 up to dm not all 0 such that d1 v1 plus d2 v2 plus up to dm vm is equal to the 0 vector. Okay, and this can be rewritten using matrices. So we have v1, v2 up to vm and d1, d2 up to dm, and this is equal to 0. So this matrix is V, and let's call this matrix D. So now we have WB equals V and VD equals 0. So now if we multiply both sides here by D, we have WBD equals VD equals 0, which means W times BD is equal to 0. And remember, B is an M times M matrix, D is M times 1, and this means that BD is also M times 1. So let's say BD is equal to E, and E is equal to, actually I'll call it F. So BD equals F, and we have F1, F2 up to Fm, where BD, so that means that W1, W2 up to Wm and times the matrix F1, F2 up to Fm is equal to another linear combination of the W, so F1, W1 plus F2, W2 up to Fm, Wm, and this is equal to 0. Okay, so this is because we had WBD is the same as WF, which is equal to 0. And since the W's are linearly independent, we are forced to have the F's must also all be 0. Okay, so all the coefficients in the linear combination must be 0. So it follows that BD must equal all zeros. Okay. So now since BD is equal to 0, And remember, we had the D, we just rewrite it. So D is equal to D1 up to Dm. But now since B equals the inverse of A itself is invertible, so this is invertible as well. What we can do is multiply both sides by A at the front, so we have BD equals 0 implies ABD is equal to A times 0, which is 0. And using associativity, we have AB times D is 0. And this is the identity matrix. So now D is equal to 0, which means that D must be equal to all zeros. However, this is a contradiction from earlier, because we assumed that not all the D's are equal to 0. So this contradiction proves that the V's are linearly independent. So we've successfully proven the V's are linearly independent. Okay, so now we can add linearly independent here. And it follows that since V's are linearly independent and a spanning set, this is a basis. So this successfully proves if you have a spanning set the same size as a basis, then the spanning set itself is also a basis. Okay, so that concludes this proof. So I hope you enjoyed this video. Thanks for watching, and I'll see you next time.